Hello, welcome to section 5.2, verifying trigonometric identities. We're going to try this a little different this time at the request of some of you students. So welcome, and this is just going to be an introduction and some of the tools we might find useful moving forward. So remember that an identity is an equation that is satisfied for all values in the domain. Um, these are going to require a lot of practice, so the more exposure, the better. So this is a great opportunity to use the book just to see more examples, whether it's just in print or the watching the videos. Let's go on to the hints for verifying identities. The fundamental identities are going to be huge, so knowing the reciprocal functions are big, and also that tangent of theta can be written as sine theta over cosine theta. Similarly, cotangent is the reciprocal. Um, Also, we're going to be dealing a lot with the Pythagorean identities, so we want to be able to not only use it in its most traditional form, but also the different variations on it. So if we look at sine squared theta plus cosine squared theta equals 1, that's just the basic identity, but there are different forms. We could subtract cosine squared over. So if we subtract cosine squared theta to the other side, then we get an alternate form, which is sine squared theta is 1 minus cosine squared theta. So that's another alternate form of this original Pythagorean identity. Also, similarly, going back to the original, we could have instead subtracted sine squared over. So that would have given us cosine squared theta is 1 minus sine squared theta. Now, these three right here are good to be very familiar with, but sometimes, like we saw in 5.1, we're also going to want these to be switched around. Because it's subtraction, we can't just switch them, because if we switch them, then we would change the signs. So the way we do that is we can go ahead and multiply by a -1, and that way we would get, for example, negative cosine theta is, now I can go and write it as sine squared theta minus 1, because now the sign is positive and the 1 is negative. So this would be another alternate form. Although I would say these two you want to be pretty familiar with. You want to be able to work to get this one. This is not something we want to necessarily have committed to memory. So now I would like you to go ahead and try to write the other Pythagorean identities in their alternate form. So 1 plus tangent squared theta equals secant squared theta, versus the other one is 1 plus cotangent squared theta equals cosecant squared theta. So just two different tricks to remember these. I like to see the similarities and differences between these. So notice that the tangents, whether it's tangent or cotangent, has the +1 with it, and then the secant or cosecant is by themselves. Also, notice that tangent and secant, neither of them have co as a part of their names, whereas here we have cotangent and cosecant. So that's kind of my more traditional way, but recently I was told a colleague uses a trick, which is I tan secretly, to remember that one, and 1 coat in the closet. But those are just ways to remember it. But let's go ahead and find the alternate forms for each of these Pythagorean identities. So one way to do that for here is to subtract the 1 to the other side. All right, and so we get tangent squared theta equals secant squared theta minus 1, and then over here, similarly, we could subtract the 1 over. So here we would get cotangent squared theta equals cosecant squared theta minus 1. So those would be the most common alternate forms. Because the plus 1 is not isolated in either of these, whenever I am trying to find the alternate forms, I always write out the original for these ones and get here. Whereas for the sine and cosine one, I want to know more automatically. And then I'm just going to show you, because I'm just looking at the paper copy right now of the notes. So that's kind of what was intended to go here on page 1 of 5.2. Then looking down at some more hints, usually we want to start with the more complicated side, and we only manipulate one side of the equation to get the other. This will make more sense in examples. Number 3, it is sometimes helpful to express all trigonometric functions in the equation in terms of sine and cosine. That is the go-to. So I feel like the main plan of attack is look for your Pythagorean identities or any of your identities that are kind of screaming out at you. And then once you have that, if things aren't simplifying naturally, we go straight into sines and cosines. Number 4, usually any factoring or indicated algebraic operations should be performed. So a lot of times we will factor, and it really depends on the situation, but let's go ahead now and practice this factoring. Sine squared x plus 2 sine x plus 1. First, I want you to see a pattern here. So off to the side, I'm just going to quickly go ahead and look if we had. This is kind of following the pattern of a trinomial, 1, 2, 3 terms of x squared plus 2x plus 1. So our sine x instead we could think of as x. So if we were trying to factor this, we're just trying to figure out what two things multiply 2x squared. So that's going to be x and then what two numbers multiply to give us 1. So that's 1 and 1. And everything's positive, so we're going to get both positives here. And we can always check that. The x squared we know works, the 1 we know works, but what we really need to check is these two inner numbers, because 1 times x is x times 1 is 1, and we have to add those together to make sure we get that 2x. We don't actually need to worry about this check as long as we are finding the two numbers that multiply to 1 and add to 2. So if we're careful about that, and there's no number in front of the x squared other than 1, we can simply say, okay, what two numbers multiply to 1 and add to 2? And that's 1 and 1. So that gives us the plus 1 in here and inside each of those factors. So remember, you can always pause the video at any point in time. If you say, hey, I want to try this on my own, pause, try it, and then you can check. So moving into our two factors, we are going to figure out, okay, well, sine squared x, that's going to be sine x times another sine x. That'll give us our sine squared x. And then now what multiplies to 1 and adds to 2. So here I like to write that out, what multiplies to 1 and adds to 2, and that's going to be 1 and 1. So my two factors are going to be sine x plus 1 and sine x plus 1 as well. So that would be how we would factor that. Number 5, as you select substitutions, keep in mind the side you are not changing because it represents your goal. And again, this is going to make more sense as we move along, but let's go ahead. Then if an expression contains 1 plus or minus sine x or 1 plus or minus cosine x in the denominator, one strategy is to multiply the numerator and denominator by the conjugate. So what we mean by this is if we have something like a 1 minus cosine x in the denominator, and this is especially true if over here we do not have a denominator or we do not have more than one term in the denominator, one common strategy is to multiply by 1 plus cosine x, top and bottom. And for this case, I'm just going to make this a 1 so we can kind of see the point here. So when we multiply the top, we're just going to get that 1 plus cosine x. But on the bottom, when we multiply this out, we get plus cosine x minus cosine x and then minus cosine x squared. So notice the cosines cancel here. So what we end up with is in the numerator, in the denominator, we end up with 1 minus cosine squared x. The beauty of this 1 minus cosine squared x is that 1 minus cosine squared x is also sine squared x. So that's kind of the whole point of doing that. So we could get it into one term. So let me just write that. 1 plus cosine x over sine squared x. I'll leave it at that for now, but the one value of having this sine squared x on the bottom is now we can actually go and distribute the sine squared x under the 1 and under the cosine x. Cosecant theta times secant theta all over cotangent of theta. So here we are supposed to simplify the expression to a constant, a single function, or a power of a function. We're trying to simplify things and we're trying to get rid of a fraction. So I don't see any Pythagorean identities screaming out at me, so I'm going to go ahead and put everything in terms of sines and cosines. So cosecant can be written as 1 over sine theta, and secant can be written as 1 over cosine theta. And then on the bottom here, we have 1, or I don't want to write it as 1 over tangent. I'm actually going to write it as cosine over sine. So cosine theta over sine theta. There's multiple strategies, but one strategy is just to take the denominator and flip it. So, and we can multiply the top together. So that's just going to give us 1 over sine theta cosine theta. But the bottom, we're going to take it, flip it, and multiply. So we're going to multiply by sine theta over cosine theta. Okay, so we have to be careful here on what cancels and what does not. So anything on the top can cancel with anything on the bottom. So therefore, in this situation, my sine thetas cancel, but my cosine thetas cannot cancel because they're both in the denominator. So I end up with 1 over cosine squared theta, because cosine times cosine is cosine squared. And this can be written, because 1 over cosine is secant, so this can be written as secant squared theta. So my final answer here is secant squared theta, which is a power of a function. All right, I hope you enjoyed the video, and I just wanted to share real quickly. I tried to do it where I was using the door instead with a panel behind it, but there was too much glare, but my kids ended up having some fun with it. So you can see their drawings, each of them. So they got to have some fun with it. But I do have a bigger whiteboard ordered. I'm hoping this works out. All right, well, I hope you enjoyed the video, and we'll be in touch soon.